I had an electronics class recently, and the final project was to make a DC motor. Most of the guys did the simple ones with the armature and the field windings and all that. Some of them used speaker magnets. A couple of them did the really simple ones with just a coil of wire that spins around. And anyway, I'd already done one of those a long time ago actually, so I decided to kind of challenge myself a little and make a brushless motor. My original design was going to have 3 coils set up like a 3-pole brushed motor with a 2 MOSFETs and a push-pull configuration on each what would be the commutator plate, right? That didn't work out so well. I was getting a lot of shoot through on the MOSFETs or leakage or something. Anyway, I didn't want to hook them together because it seemed like I'd just fry them right out. So in a frantic rush on the night it was due, I came up with this. This is a censored brushless, pretty simple. It's got a US 1881 Hall sensor up here with I think it was a 10K resistor across it. I've got let's see, what is this? This is a 30N06L NPN or N channel power transistor or MOSFET, metal oxide semiconductor field effect transistor. Basically just a big ass transistor. And I got one big diode over here. And the purpose of that diode is that when I energize these coils and then I take power off again, that magnetic field collapses and it makes a little power surge in the other direction. It's called BEMF, or back electromotive force. This field here collapses, and that influences this coil here through inductance to send a brief burst to relieve that power surge, basically, into little neon bulbs. And it turns out that MOSFETs really do not like back EMF. And if you feed it to them, they will stop working. And mine stopped working, so I replaced that and put that in, and that just eats that up, and it seems to run alright since. So, demonstrated here, I've got some batteries. Some people might recognize these as coming off the fail cart. And the motor I was going to build, I was hoping I could power an RC car with it. It would be, you know, self-starting and torquey and all that. This thing ticks over and that's about it, but this magnet in here is a 5/8 by 5/8, if I remember correctly, neodymium magnet. It's diametrically magnetized, which means it's magnetized on either side instead of the ends, which is more common. I got it from K&J Magnetics. Price wasn't too bad. It's a powerful little bastard. The first case I tried to put it in, I had steel cores in the coils, and that didn't work out too well. It liked the cores so much that it didn't care what I did with the coils. It was just stuck to them, and there was nothing I could do about it. I formed these coils with, I think it was about 32 gauge wire that I pulled out of a CRT television, or a computer monitor actually, where it was used as some kind of RF shielding behind the picture tube. Anyway, I just pulled it out of that, wrapped it around the bottom of an epoxy bottle, pulled it off, and stuck it on a board here. I had a big piece of hot glue, like a big stick. I've got a little hot glue gun that didn't fit into, so I just cut it and then used it as a spacer in here, and it actually holds pretty well. It's kind of funny, you can see when it runs the coils actually move. I can get it on here, right? There we go. Of course, how it runs depends on the timing. if I get it too far to one side or the other, I imagine the coil starts interfering with the Hall sensor. And yeah, the Hall sensor I used is what's known as a latching Hall sensor. It basically, you can think of it as being like a light switch with a magnet on the end of it. So you pull a magnet close to it, and let's say it turns on the light switch. You pull it away, the light switch stays on until you come back at it with the magnet turned around. And so basically what this means is that for half of the magnet going around, the Hall sensor is on. For the other half, it's off. And by on or off, I mean the output is high or low. That output feeds the gate on the MOSFET, which allows power through the two coils. So this is another type of brushless motor. It's not one that I've made, but I found a lot of them. It's an AC induction motor. This just takes mains current from the wall, 110, 120 volts, and energizes the coil. And you got this funny little rotor in here. And I've read a bit about how these work, and I tried to read the bit in the textbook for the electronics class. It's something to do with phase angle with this versus, I think it induces a magnetic charge in the, or magnetic field in the rotor, and then when it changes, it forces the rotor to move. You find a lot of these, mostly because they have a very long service life. There's really nothing to go wrong here. I found them where the bushings were worn out or dirty or dry, and it's just a matter of cleaning and relubing them and they're good to go again. Here's another AC induction motor. This one came out of a fruit juicer. Looks like it's got 2 coils of wire in it. Maybe. Yep, it's got 2 coils of wire. It's unusual. I did notice this one has a lot more torque than you usually see with these. One interesting thing with it, it doesn't always spin in the same direction. In the juicer, we figured that was just a feature, but now I realize it kind of depends on where the rotor stops. I'm also just now noticing that it's got this funny little wobble when it stops. Like residual. I don't know, it's got a pretty powerful field even as is, so it's probably got an actual magnetic core in there. Huh, might tear this one down sometime. Here's yet another one. This is out of the same microwave as the fan. This is a little gear motor. This is what turns your food around and around for cooking reasons. It's torquey, it's quiet. Sure, I'll find a use for it somewhere. But they aren't all small. I don't know what this one came out of, but it's pretty damn big. Torque is decent. Nothing to write home about, but decent. And again, it's quiet. The service life is limited only by the bushings. If you really want to see a big one, I don't have the rest of it with me, but this used to power my dad's hot tub. Bearing in the front, the bearing in the back. It had the coils all around the outside, a starting capacitor back here. It's got this cool little governor deal here, which controls the starting. When it kicks on, this pulls in, because these pieces are slung out, so this pulls in. And when that pulls in, it undoes a set of contacts, and I think it just changes the way that the windings are connected around it from a starting configuration to a running configuration. Incidentally, if you hear somebody say something's running balls out, governors like this used to just use like metal balls hanging off and they'd sling out, and so balls out would be as fast as it could go. You can use governors like this you know, varying to hook up to a throttle cable or a steam valve or whatever. We may put it back together and repurpose it to something else, but can't remember the last time we needed a gigantic motor laying around. So when I said I made a motor several years ago, this is the one that a friend and I made in the 6th grade. Did a little work on it later to use it for another school project, put the crappy brushes on it. It's just a 2-pole motor. You never see these in the wild. I mean, you never see these actually installed in something. They're not self-starting. They're not terribly powerful. By self-starting, I mean you can't just plug them in and they'll run. It's really just an experiment in, you know, electromagnetism. It's set up. These are just 2 big bent nails. So there's a coil going all the way across. So there's 1 pole here and 1 pole here, and then as this turns, it goes into the poles. One of the commutator plates, in this case, is just a strip of wire, and then the other one is actually a thick piece of copper house wire that I hammered flat and put in, soldered up. The other one overheated and flung off, if I remember correctly, so I don't know how long this will run, and it won't run well, but cool thing with winding a motor this way, you can use an AC power supply. This is an old Lionel transformer one of my friends gave me a while back, and should work pretty well. So let's try it on about 10 volts. Come on. There we go. So yeah, you can see it's got just a little bit of brush arcing going on. If I remember right, one of the groups making motors in the 6th grade class decided to try and build theirs into a bomb. They covered it in hairspray and tissue paper, and unfortunately it quit running just before they were gonna get it to catch fire. Oh, there goes the other comm plate. Fell off. And here. Yeah, solder melted. And you know, obviously brush motors that are actually used in things don't have this kind of sparking going on, but you still have this connection that has to slide and make a connection and break a connection, and you're always going to get sparks there. You're always going to get arcing, and you're always going to have the commutator wear out. On most motors this isn't much of an issue, well, because it takes so long for it to wear out because they're not built by a 6th grader.